capital psi be the psi function of your whole system. You've got big N particles now in your system. So particle 1, its position vector, so we're talking three-dimensional space now, okay, will be R1 vector. The little wiggle under the letter tells you that it's a vector, right? So there's a position. So you think of the position as like an arrow from the origin of your coordinate system to the point where the particle presumably is, right? So your big psi function, capital psi, if you like, psi, is a function of the n coordinates and time. Now, if the conditions we're talking about, there are no interactions, everything is independent of each other, then presumably this capital psi function is just the product of the individual psi functions. So here you've got psi 1 and its parameters would be r1 of time times, that psi function, times psi 2 and its parameters are r2 and time and so on, dot dot dot, and finally the last one, psi of n, its parameters are r of n and time. Okay? Now why does that assumption, why does that seem reasonable? Well, because if you square this, using the same Born model, we're carrying over as much as we can from the one particle case to the n particle case. So the same Born, B-O-R-N, probability density model in interpretation of quantum mechanics. Okay, so if we assume this is the case, then the probability that particle 1 is in volume d tau 1 and particle 2 is in volume d tau 2, etc., will be this, right? Here's your probability density, and here are your volumes, like dv1, dv2, dvn, okay? And presumably that is just this. Right? Because what's the probability that particle 1 is in this volume d tau 1? Well, just the probability density for particle 1, right? Which is just little psi 1 squared dt1, and the probability that particle 2 is in volume d tau 2 is little psi 2 squared, and so on. Okay. So this is now a generalization from the one particle system to an n particle system, and in this case we're assuming no interaction and each particle is just completely independent, and hence your amplitudes now, because these psi functions are sort of amplitudes, right? Remember, an amplitude is something you square to get something physical. Now why does that seem plausible? Well, Think classically. Think just a little statistics, probabilities. If you have two events, and the probability of one event happening is p1, and the probability of another event happening is p2, and those two events are totally independent, and let's say over a certain amount of time, what's the probability of getting both those events happening? It'd just be the product of the two probabilities, p1 times p2, when you have independence, you just multiply the two probabilities. So the probability of 1 and 2 happening is the probability of 1 happening times the probability of 2 happening. So similarly, what's the probability of finding the particle 1 in this volume, d tau 1? What's the probability of finding the particle 2 in this volume, d tau 2, etc.? And they're all independent of each other, so you just multiply them. You multiply the probabilities. Well, that's what this is, probability p1, right? It's the probability density times a volume. That gives you a probability. What is probability density? It's the probability divided by a volume, right? So so you've got a probability divided by a volume multiplied by a volume. That just gives you a probability. So this is your probability 1. That's your probability 2. Dot 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 probability n. So this well, this suggests no, here. This makes sense because it fits with our classical model, our classical intuition that you multiply independent probabilities, right? So we have a model now for what your the psi function is for a multi-particle system. In the case of independence, the particles not interacting independently of each other. It's just the product of the individual psi functions. Right? So that's our first assumption. Okay. Now, how about the Schrödinger equation? What would that be? Well, before we just had one particle, right? So big N here was just one. So you can forget about this sigma, sum sign, and so the I here is just one. So you've got mass 1, del squared, just 1, and the potential acting on that particle is just V1, the potential on that particle, and your position is just 1, okay? And this would then just be an individual psi, it would be psi 1, it would be this thing, this one, okay, equals E psi 1. Well, now this is a kind of hypothesis, really. You're in a sense just throwing it. Well, I'm throwing it at you in a sense. So when you start thinking about the multi-particle system, it seems a reasonable hypothesis that this would be your Schrödinger equation. Okay. Now you've got capital psi, so this is now a wave function for n particles. You've got like 3 dimensions for each of these. So this wave function is acting now in a 3 times n dimensions. Right? Now this is, if you remember from earlier lectures, this was one of the, based on this, the multi-particle wave function. This is one of the objections that Pauli had against Schrödinger's idea of a pilot wave for Schrödinger and de Broglie. So Pauli was saying, well, your pilot wave is a physical wave in 3-dimensional space. That quantum mechanics, that the Copenhagen school, Bohr, Pauli, Heisenberg, and so on, they were developing this kind of stuff, multi-particle systems. So that they knew the wave function, the multi-particle wave function, was far more abstract. wasn't a fairly simple 3-dimensional wavicle or like a surfboard pilot wave kind of thing. They knew it was more subtle than that. It was multi-dimensional, and you can see why, because this psi, capital psi here, is a function of like n position vectors, right? So it's like 3 times n, big N, parameters in your space, plus time, so 3n plus 1, okay? All right, so, well, here's your hypothesis for a multi-dimensional Schrödinger equation. Your del squared I, so that would act on particle I. In other words, this acts, so you're differentiating twice with respect to x and y and z on this variable here, right? Now, if there's no interaction between these independently, then this splits up into n equations of our old form that we're used to here. If there's no interaction between the particles, and where these EIs, the eigenvalues for each individual particle, but you can sum them to get your big E for your capital psi, for the wave function for the whole system, right? Now, I don't know how plausible that sounds, but that's where multi-particle quantum mechanics has gone. This is more hypothesis than anything, but it fits the experiment very well. So it's doing something right. Again, what does it mean? And the real fun starts when you drop the hypothesis that these particles are not interacting. So when you start assuming they are interacting, and another hypothesis that these particles are no longer indistinguishable, are no longer distinguishable. In other words, they are indistinguishable. You can't tell the difference between them. Like, imagine you had two electrons, right? Electrons are identical, right? They have identical properties, as though they all came out of the same mill at the Big Bang or whatever. So I've always been deeply puzzled by that. Why do you have so many zillions of copies of the same kind of particle? The neutron, the proton, the electron. So why does each category of particle, why are they all the same? So like identically the same. So when you drop the idea of distinguishability, so in other words, now you have multi-particle systems of particles that are indistinguishable. You cannot tell the difference between them, right? That's where the fun starts, and that will be for next session.